Okay, so we're going to start the introduction to electrolysis here. So an electrolytic cell literally does the opposite of what a voltaic cell does. In a voltaic cell, you use a chemical reaction, a redox reaction, to generate electricity. And you can use that electricity to drive something, like a motor or an electronic device. Here, we're going to build cells that go the other way. This time, we're going to pump electricity into the system and push a reaction, a chemical reaction, to go the opposite way. In other words, we're going to take a non-spontaneous reaction and drive it with electricity instead of taking a spontaneous reaction and extracting electricity. So it basically just pushes the chemistry uphill, if you will. A couple important things to note is that the terminals of an electrolytic cell in terms of the positive and negative are flipped. So just to kind of compare that, in voltaic cells, the anode was negative and the cathode was positive. What's still always true in all cells, whether they're voltaic or electrolytic, is that the anode is still where the oxidation happens and the cathode is still where the reduction happens. So that's still true in both cases. Anox, red cat, just to help you remember that. So for example, if we were to look at this kind of like an image, just so we can compare to what we've said in the past, I'm just gonna, let's see, go to a picture here. Here we see a galvanic voltaic cell, the spontaneous kind, and the chemistry is producing the flow in a specific direction, and the electricity is being generated. In this, it's the same reaction but run backwards. So this time we're providing the energy to make the reaction go the other way. Notice a very important fact. When you write a traditional voltaic cell, your cell potential is positive, which indicates spontaneous reaction. But if we reverse the reaction, the cell potential becomes negative, which means it's not spontaneous. It's the same number, but just negative, which means this is the minimum voltage we would need to provide to push the electricity, to use electricity to push the reaction the other way. So this is the difference between water running down a hill because of gravity or pumping water up the hill using a machine and making it go the other way. The energy you would get out is kind of the same energy you have to pump in. Now this is voltage, not energy, but you get hopefully my drift. Now really it takes more than this. This is like the minimum line, but there's something called the overpotential, which is kind of like the activation energy that you need to go, that's like the minimum, and you would have to push a little harder. It's also the same idea of if you're pushing a box up a hill, you have to account for friction, right? You need more than just the minimum energy typically. But this kind of defines that limit to reverse the reaction. So what do we use these kind of cells for? Where am I looking? Sorry, I'm in the wrong thing. You can use electrolytic cells for purification of metals. That's one application, and I'll show you that in a little bit. You can use it for electroplating. So like when you have, let's say, silverware at home and it's silver plated, you can use electricity to drive the plating reaction so you can put one metal like silver on a more base metal like, say, copper or zinc or something. You can also use it for separating or ions and reducing them to, let's say, like for example, sodium. When you want sodium metal, which is such a reactive metal, you take sodium chloride and you melt it, and then you can use an electrolytic cell to literally separate the sodium and the chlorine. You can get the sodium in its metallic form, you get the chlorine in its gas form, and get it that way. So there's a number of applications that you're going to learn from this. I'm going to start with one typical type of problem today, which is a really simple calculation on kind of an electricity stoichiometry, if you will. Here, we need a few definitions of units so that this all makes sense. So what we've been calling potential is measured in units called volts that you would learn in physics. The volt is defined as the joule per coulomb. meaning energy per unit of charge. So you can see it in units here, J over C. A volt is 1 joule per coulomb. And then the other thing we have to understand is the flow of electrical current is measured in amperes, or amps for short. A amp is by definition the amount of charge, really or the number of coulombs that flow per second. So if you picture like electricity like a river, you can think of the current literally like how a stream would be flowing along, and the faster it flows, the more water that moves per unit time. And here we're not flowing water, we're flowing charge. But those units have to be clear so we can understand the problem I'm about to show you. So I'm going to actually show it to you in a visual way, just so you can really understand what's going on. So let's take a piece of copper, and I'll start with 10 grams, it's good, I think. And then on the other side, I'm also going to put a piece of copper. So I'm going to show you one way we could purify kind of a raw metal with electrolysis. And then I'll show you how to do plating. But it's the calculation that I'm most interested in right now. And let's put this in a copper nitrate solution. So what I want you to look at here is that we have copper. And clearly right now the potential would really be essentially zero because there's no difference. It's the same reduction potential for copper and for copper, right? So what I want to show you is what happens over time if we put some voltage into the system, enough to drive a current, and let's make the current 2 amps, and let's let it run for 5 minutes and just see what happens. And let's see if we can figure out what's going on. Then I'm going to show you how to do some math that matches what we see happening. All right, so I'm going to run this now, and it doesn't actually take 5 minutes. This is like a simulation, it goes faster. But watch what's happening inside the device, and then we'll try some other ones. Here we go. So at the red terminal, which is the positive one, you'll notice that pieces of or atoms of the metal are losing electrons. They're being oxidized. And those electrons are being pushed to the other side. And copper ions are being reduced on this side. You'll notice that this piece of copper is shrinking, but this piece of copper is growing. You can even see it getting thicker on the bottom. What's going on here? Like just describe it to me, and we can get it into like the nitty-gritty in a minute. But let's just tell me, what is actually happening here? What is the electricity doing? And it ended, by the way. So. Can you tell? Oops.
It looked like the electrons were going in like the opposite direction that they would usually go in, because they were going through the red wire, which is usually the negative terminal,
Mm.
instead
So
of coming out that way.
yeah, so definitely we were pulling electrons off of copper at the positive terminal, and the device, which is just a power supply or it could be a battery, is pulling the electrons off against their will and pushing them onto this side, and the copper ions in this vicinity are picking them up and literally reducing to neutral copper onto the actual electrode. And so this electrode gained weight as this one lost it. And the copper ions in the solution that are already present are just there because it's more efficient this way, since we want to cause the copper to be reduced or plated. Now imagine if this piece of copper was kind of like not purified, like we just kind of got it out of some ore and it's kind of really junky, crappy copper. What's going to happen through the electrolysis process is the actual copper atoms are dissolving. Any kind of junk that's not supposed to be there will just fall off and sit in the bottom. But then pure copper is being plated onto this piece. And if we do this over time, we can literally purify the copper sample by doing this electrolysis experiment. We can continuously take copper from kind of the raw sample, dissolve it by pulling electrons off, and then at the other end take those same electrons and put pure copper atoms right onto the sample that we want to make purified. So again, this is an industrial technique that is used for purifying metals that are extracted from the ground. Now let's look at the actual mass change and see if we can figure out what happened here. So we got to look at the data on this, and I'm going to kind of split this into two so we can do it together. So this is one of the kind of typical types of calculations you have to be able to do in terms of electrolysis. The question might ask, well, if this is the current and this is how long you run it, how much copper will be plated? So given that we are running 2 amps of current for 5 minutes, the question is, what mass of copper is, we could say, reduced, or we could say plated, or there's a lot of ways we could say the question. But the essence of it is this: we have to put the numbers together in what's a pretty simple dimensional analysis problem. So I'm going to start with the time, which is in minutes. But since I know my ampere is coulombs per second, I need my time to be in seconds. So I'm going to kind of set up a conversion here. There's 60 seconds in a minute, right? Then I know that my current, my electrons are flowing at a rate of 2 coulombs of charge every second. So if I stopped here, I can calculate the total amount of charge that has been transferred. Here's the important step that starts to put it into kind of the chemical realm. We had referred to something called the Faraday's constant when we did the Nernst equation and some other stuff last time. And what that relates is the number of coulombs of charge in 1 mole of electrons. So a single electron has a definitive amount of charge measured in coulombs. When you take 6.02 times 10 to the 23rd electrons, which is a lot of them, it adds up to quite a bit of charge. But what this allows me to do is translate between the total number of coulombs of charge and how many moles of electrons were transferred. So in this case, if I now say, okay, I need the coulombs here and I put the mole of electrons here, 96,485 coulombs of charge per mole of electrons. I'm going to kind of expand this now, I need the room. At this point, I will have counted the total moles of electrons transferred in the process that we did over the 5 minutes of electrolysis. But we want to turn this into the copper being plated, which is governed by this half reaction, right? It's aqueous copper ions being reduced by 2 electrons to become solid copper atoms. So what we can see now, and this is a key point of why we need to know the half reactions, there's a relationship between the moles of electrons and the moles of copper. You can see it's a 2-to-1 ratio. So now we can see that for every 2 moles of electrons, we get 1 mole of copper production. Does that make sense? Right? Because it takes 2 electrons for every 1 copper in this reaction. And once we know the moles of copper, of course we can find the grams of copper because we know the molar mass is about 63.55 or so. So once all is said and done, we'll have the grams of copper that should have plated, ideally, over the time that we delivered this amount of current. So 5 times 60 times 2, divide 96485, divide 2, and then times 63.55, I get about 0.198 grams. Okay? Now if I go back to the simulation, remember we started with 10 grams on each side, right? Notice this side, where the reduction happened, has increased its mass by 0.198 grams. That's how much copper we were able to electrolyze and really reduce onto the right side. If we look at this lost the same amount of copper. In fact, if you do 10 minus 0.198, you get basically this number. So in as much as we were doing this reaction, we were taking something that if we just let sit there, would have zero potential to go either way. And by attaching the positive electrode to this piece, we pulled the electrons off and forced them to this side. So we kind of forced an oxidation reduction reaction that was not going to go on its own. Right? This one wasn't going to go backwards or forwards. It was just going to sit there. But we pushed the electrons in a direction using our external power source, and we forced a reaction at both sides. We forced really this reduction at one end. Actually, let's write this out so we can see this more clearly now. Actually, well, it would be smart if I did something like this, just so I can label it more clearly with you. 1 segundo, please. Whoops. Sorry, I need the space to make this. There we go. All right. Shrink that real quick. New here. Okie dokie. Like this. So I can label it right on the diagram with you. Come on, you can do it. Copy, paste, copy, paste. All right. So let's do some labeling here and make sure we understand what just happened. So this is the positive terminal, and this is the negative terminal. We saw that the reaction, happening here was copper becoming copper ions and 2 electrons. So this is oxidation, and this must be the anode. And again, we said for this electrolysis type cells, electrolytic cells, the anode is the positive terminal. It pulls the electrons out. The electrons then flow in this direction in the circuit to the other side, where we're taking the same electrons and taking the copper ions in the solution, adding the electrons to them to produce the neutral copper that's forming on here and plating it. So that's why this is our reduction reaction, and this is our cathode, which is our, in this case, negative terminal. So you'll notice here, where the reduction happens, the mass increases, meaning we are getting metal to plate onto this terminal or onto this electrode. On this side, the mass decreases. And what's interesting, the amperes tells me how fast charge is being transferred. And then the time tells me how long the transfer of charge is happening. And if you understand that, then you can see that if I turn this device on longer, I would have gotten more metal to plate over. Or if I raised the current, it would go faster, so again, I'd get more metal proportionately. The voltage just has to be enough to drive the current. Now, how do I know what enough is? Well, in this case, there was a zero potential difference in the ideal sense of copper versus copper. So I just needed any voltage to really get it going, and the higher the voltage, the more current I would ultimately drive. But in some cases, the reaction wants to go one way, but we have to push even harder to force it back. But I thought this would be a nice, easy one to start with, so I figured I'd start here. What do you think so far in terms of the calculation or the concept of this process? Questions? Let's try one for you. So let's set up a different reaction this time. So this time, let's go with, so what's going to happen at the positive terminal every time on these? Is it going to be oxidation or reduction? What's it going to be?
Oxidation.
Oxidation. So if I look at the reduction potentials of these metals, silver really likes to be reduced compared to the other ones. So let's force it to be oxidized. Ha ha, silver. And if we compare that to copper, copper has a lower reduction potential than silver. So the natural state of affairs, if I put copper and silver in a reaction together, would be that the copper would oxidize and the silver would get reduced. And in fact, we could calculate that cell potential. It would just be the difference between these. It would be, what, 0.56 volts driving it in that direction. Now, let's say my goal is to silver plate the copper. So I'm going to put silver in the water, so a silver solution. That way, what's going to happen here, maybe I had to reset this. Let's see, probably when I turn it on. What's going to happen here is that we are going to take these silver ions and plate them on the copper, and the silver ions, as we deplete them, will get replaced because that's why we put this silver on this side. So now it's a source of silver that can be oxidized and put into the water, and we can keep the process going. Let's change the amperage this time to 5 amps, and let's crank this up to 10 minutes. And before we run it, I guess I had to do this first. I'm sorry. Let me set that up again. I probably should have looked at that first. Oops. All right. What did I say? This was going to be 3, or I think I put it to 5 and 10, right? All right. So I'm going to set this up. Oops. And I want you guys to predict what mass of silver. So we're going to do this kind of problem again. Okay? But we've changed the numbers. So now it's 5 amps running for 10 minutes. And we want the mass of silver. And you got to be careful here because this time the reduction reaction is that silver ions, which are positive 1, take 1 electron each to make silver metal. That's the reduction side. And that's going to actually happen directly onto the copper metal. So in this case, silver is both being oxidized and reduced in this situation because we're oxidizing the silver at this end to get it into the water more, but we're reducing it onto the copper metal as we plate it. All right, you want to take a minute and see if you can do the math, and then we'll run the simulation and see if you match. So here is the essence of the setup. And then the only other thing you might see different is we might have to go backwards. Like if I told you how much was plated, can you tell me how long it ran? Or can you tell me what the current was? But we'll do one of those after and then probably call it a day for today. Get a little bit more into the theory behind this next time. Of course, there could also be hours instead of minutes. Then you'd have to account for that. I'm just trying to go through and kind of show you what I'm changing. It's like 107.9, isn't it? Silver, yeah, close enough. All right, I got an answer. Did you guys get anything? Still going. That's all right. Okay, Imelda, I see your answer. Let's see if the simulation agrees. This is the exciting part. Dun, dun. Oh, whoops, I forgot to raise the voltage. There we go. So if you're right, the mass on the copper electrode should get up to like 13 and change. And we should see silver on the copper. So it should start turning like a silvery color on the surface. Again, this is like what happens with silverware. You take a spoon that's, say, made out of steel, you put it at the negative electrode where you want the reduction to happen. Then you put the silver metal at the anode, put it all in a silver solution, and then you drive it with the electricity until you get a coating. The longer you wait, the thicker the coating you get. Now, the quality of the coating is dependent on how carefully you run the experiment, the nature of the setup. If you go too fast, there's more to it than we're saying. We're just looking at the basic theory of the chemistry. We're not looking at how would I do this in my house and actually make beautiful silverware. Okay, I mean, it's a little bit more complicated, but you can see the simulation at least gives us some inkling. And as you can also see, you had what, 3.35. I had the same thing. This is just a little bit higher. So I don't know what, in terms of what they're using for molar masses and stuff, it could be a little different. It's fine. But the basic essence of it is right. You did it correctly. All right, let me give you one more to try. I don't know that I can simulate this one, but at least we can write it out. So let's say the current was 6 amperes. For how many minutes would we have to run it if we want to reduce, let's do 20 grams of zinc metal. So in this case, I want us to find how long would we have to run the device. So how does this look different? Well, we're starting from the end this time. We're starting from the mass of zinc, and we have to set it all up the other way. So the first term would be the 20 grams of zinc. What would be next? Like what should be the next term here if we're trying to run this problem backwards? Hala.
You would divide by the molar mass.
Yeah, oh, okay, Kirsten. I'm just going to set it up by, that's exactly right, because the grams go here and the moles go here. Each mole of zinc is 65.38 grams. And if we stopped here, we'd have the moles of zinc. But if we look at the reaction, for every 1 mole of zinc, we need 2 moles of electrons. Right? It takes 2 moles because of the charge. Now we know the moles of electrons. Well, from this stage, we know that every mole of electrons carries 96,485 coulombs of charge. So at this point, we would have calculated the total charge transferred. It's a little sloppy, sorry. Now at that point, we could figure out that every second we're delivering 6 coulombs of charge because that's the amperage. So that's an S. That's where the current comes into play. And once we know it in seconds, each minute is worth 60 seconds, and we could figure out our final answer in minutes, hours, whatever we want. So we literally just set it all up backwards by following the units through. 20 divided by 65.38 times 2 times 96485 divide 6 divide 60. This would take us about 164 minutes. Or if you like, about 2.7 hours. But again, this is just to show you effectively Faraday's law of how the electricity is stoichiometrically involved in the reduction process here when we do electrolysis. That we can relate the amount of material to the amount of electricity and the time used to produce it. And I think that's as far as I want to go with that today. I think that's a good place to stop. Any questions going forward?
I have a
Oh, go ahead.
quick question. Sorry, I have a
No,
quick
yeah.
question about the AP exam. Just do you know when the results are gonna come out? Because somebody told me they'd be out in like August, and I was like, no freaking way.
I don't think so. I mean,
Okay.
considering that usually they're right around July 4th, like around that weekend, but
Okay.
that would be the people that took it May 7th, right? Like the original date that was the
Mhm.
paper and pencil. Given that this is mostly multiple choice, I'm assuming they can grade it a little quicker. I don't,
Mhm.
let's do the same delay effect. So if the original exam was a couple weeks ago, this might be a couple weeks later. It might be mid-July
Okay.
potentially. I'm guessing, but I don't know that I have an answer for that.
Okay.
Yeah.
Cool.
So
Thank you.
tomorrow, oh, I'm sorry. I'll just say tomorrow. Then we'll start the first half by going over some more of the multiple choice of that test, and then the second half, I'll probably do the next piece of the electrochemistry. Actually, let me stop the recording now because what I'm saying is irrelevant to that.